Here are the answers for the section 7-5 assignment. On page 266, we're asked to simplify expressions that have radicals. To simplify a radical expression, we have to make sure that the four rules on page 265 are satisfied. So to simplify radicals, you have to look at the four rules to figure out which of them apply to the expression that you have. In this first expression, I have an integer in the radical. So it's the first rule out of the four that's important to me. If there are factors of 12 that you can take the square root of, then this is not simplified. And that is the case. There is a factor of 12 that has a perfect square root. It's the number 4. So the technique is to rewrite this as the square root of 4 times the square root of 3. Then evaluate the square root of 4, which makes 2, but leave the square root of 3 in its radical form. Here is the simplified version of the square root of 12. Number 3 is also a radical that has an integer under the radical symbol. So it's the first rule that we have to worry about. The cube root of 16 does not produce an integer. But there might be a factor of 16 that does have a cube root. And there is. One factor of 16 is 8. And 8 is a perfect cube. So the technique is to rewrite this as the cube root of 8 times the cube root of 2. I hope you agree 8 times 2 is the 16. This is just another way to rewrite the original problem. Now evaluate the cube root of 8. It's 2, but leave the other piece in its radical format. Here's the simplified version of this problem. Number 5, we want the cube root of negative 125. Again, there's an integer under the radical. Can we find the cube root of negative 125 without making a decimal? We can. The answer is negative 5. Number 7. This is a little more complicated than the ones that we had before. We have a variable in the radical, and there's a rule on page 265 that applies to that. And we have a fraction in the radical, and there's a rule on that page about fractions. So let's do some rewriting. Here's the negative sign, and then let's separate the numerator and denominator. This is equivalent to our original problem. Now let's do some work in the numerator. If you try to take the square root of 2, that would create a decimal. So we want to check if 2 has a factor that you can take the square root of without getting a decimal. There is no factor other than 1 for which that is the case. So we're not going to break up the 2 into a pair of factors like we had done in question 3 or question 1. Now let's look at the variable piece. The second rule on page 265 addresses that. Our root is a square root. Can you take the square root of a to the second power? You can. You just get a. In the top, we have our negative sign, and then a, and then the square root of 2. In the bottom, we can evaluate the square root of 9. It makes 3. Here's the simplified form for number 7. We could find the square root of a squared. That makes a. But we couldn't make the square root of 2 produce a whole number, so we left it in its radical form. We could evaluate the square root of 9. It makes 3. Number 9. It's the third rule on page 265 that addresses the situation of a negative exponent. Let's rewrite this problem and use the meaning of a negative exponent to write this as 1 over 8 to the 5th power. Then let's rewrite again and separate it into a numerator and a denominator. In the numerator, we can find the cube root of 1. It just makes 1 because 1 to the third power is 1. In the denominator, we need to do some factoring. We try to find the cube root of 8 to the fifth power, but because this exponent is not a multiple of the index of 3, this won't work out evenly. So let's rewrite this as the cube root of 8 to the third power times the cube root of 8 to the second power. This denominator is the same as this one, but I've broken it up or factored it into two factors. Next step, here's the 1, and then in the denominator, we can find the cube root of 8 cubed. It makes 8. The other one we'll leave in radical form. Next step, let's do some more work on that denominator. 8 squared is 64, so we can rewrite this as 8 times the cube root of 64. What do you get when you evaluate the cube root of 64? That makes 4, because 4 to the third power is 64. And so the final simplified version is 1 over 32. Number 11 asks if this expression is rational or irrational. We're not going to decide this until after we simplify it. So first step, let's combine the numerator and denominator under one radical symbol. In the questions above, we occasionally started with this format and then would separate them into separate numerators and denominators. We're just doing the reverse process. Then divide the 8 and the 2, making a 4 inside the radical. Now, can you find the square root of 4 and produce an integer, not a decimal? You can. The answer is 2. Because we get the number 2, we can say that this is rational. 2 is a rational number. It can be written as the ratio, 2 over 1. Irrational numbers are when you can't write it as a ratio of integers. Irrational numbers still have radical symbols in the final result, even after you've simplified. Page 267, we're asked to use a calculator to approximate to 3 decimal places. These 3 questions, number 1, 3, and 5, are simply a matter of typing this in the calculator. So you got to figure out what button does the square root symbol, type this in and hit enter. To 3 decimal places, this one is 33.941. The next one is 13.416. And the next one is 0.775. Number 15, we're back to the simplifying kind. So pay attention to the 4 requirements on page 265. Try to figure out which one of those requirements apply to the situation you have. There's no variables in here. There's no negative exponents, but we do have a fraction. So let's separate the numerator and denominator so we can work on them separately. In the numerator, can we get an integer when we find the 4th root of 16? We can. That makes 2, because 2 to the 4th power is 16. In the denominator, is the 4th root of 27 an integer? No, it's not. That would make a decimal. So let's leave it as the 4th root of 27. On page 265, the 4th requirement for simplified form says you cannot have a radical in the denominator. This one does. So we need to rationalize the denominator. Here's how you do that. You multiply top and bottom by the same thing, and what you need to multiply by is something that will make the denominator turn into something that you can find the 4th root of. We said that 27 was not a number that you can find the 4th root of. What is the first number that's a multiple of 27 that does have a perfect 4th root? That number is 81 because the fourth root of 81 is 3. So let's multiply the bottom by the fourth root of 3 and the top by the fourth root of 3. In the top, we'll get 2 times the fourth root of 3. And in the bottom, we will get the fourth root of 81. That's why I chose this number to times by, so that I would end up getting fourth root of 81. Now keep the top the same, and in the bottom, the fourth root of 81 makes 3. Here is simplified form. It follows all 4 of the requirements on page 265. Number 17, we want to go 4 times the fifth root of negative 64. Let's first determine if negative 64 has a fifth root that's an integer. It doesn't, because there is no integer that you raise to the fifth power to get negative 64. Let's try factoring this, or splitting it up into pieces, where one of the factors is a number that you can find the fifth root of. How about using negative 32 times 2? Negative 32 times 2 is still negative 64, and by splitting it up this way, this part will produce an integer. We get 4 times, and then the fifth root of negative 32 is negative 2. And then we have times the fifth root of 2. Final answer will be negative 8 times the fifth root of 2. Number 19, let's find the square root of 32x to the fifth power. First of all, is the square root of 32 an integer? No, it's not. So we need to try factoring. That means split it up into pieces. Let's go with 16 times 2. The reason I chose that is 16 is a number that you can take the square root of and get an integer. Now let's look at the variable. This is x to the fifth power. Remember, a square root has an index of 2. It's just not shown. Is x to the fifth power a multiple of that index of 2? It's not, because this is an odd and this is an even. So we even need to factor our variable, or split it up into pieces. Let's go with x to the fourth power here and a single x over here. X to the fourth times another x is still the x to the fifth. Now here's why I factored it in that way. The square root of 16 makes 4, and the square root of x to the fourth makes x squared. And then the other thing stays in its radical format. Here's simplified form. Number 21, we want to do the cube root of the stuff that's in the radical. Is the cube root of 32 an integer, or is it a decimal? It's a decimal. So let's try to factor it and see if we can come up with a number that we can find the cube root of. Should we go 16 times 2? Nope, because doing the cube root of 16 doesn't make a nice answer either. How about 8 times 4? Yep, the cube root of 8 will produce an integer. It'll make 2. So let's go 8 times 4 is the 32. Now let's look at the letter x. Is the power on the x a multiple of that index? And it is. So I'm going to leave the x to the third power as it is. Now let's look at the letter y, which only goes to the first power. That is not a multiple of 3. And so I'm going to put the y over here with the 4. It's something that I can't take the cube root of and get a nice output. Okay, we're ready for the final answer. The cube root of 8 makes 2. The cube root of x cubed makes x. And then the other factor stays in its radical form. Number 23, let's take the fifth root of these letters. Because a to the 6, because the 6 is not a multiple of the index 5, we need to factor it, or split it up into pieces. Let's choose a to the fifth power and then a. A to the fifth times an a over here is still a to the 6, But by breaking it up in this way, I will be able to find the fifth root of a to the fifth. Now b to the fifth, I'm going to leave that in this radical. Now we're ready for the final answer. The fifth root of a to the fifth is a. The fifth root of b to the fifth is b. And then the other thing stays in its radical form. Number 25, we have a fraction in there. So let's split that up into separate numerators and denominators. The fifth root of 1 just makes 1, because 1 to the fifth power is 1. Let me copy this down here. Can we find the fifth root of a squared? We cannot, because the power on the a is not a multiple of that index 5. If this was a 5 here, then we could find the fifth root of a to the fifth. Or if this was a 10, we could find the fifth root of a to the 10. Or if this was a 15, we could find the fifth root of a to the 15. But we can't find the fifth root of a squared and get a nice output. We need to rationalize the denominator. We're going to times top and bottom by the same thing. Now, what do we need to times by? We need to times by something that will make a nice output in the denominator. I'm going to times by the fifth root of a cubed, and in the top. In the top, we get 1 times the fifth root of a cubed, and in the bottom, we have the fifth root of a to the fifth. And now you see why I chose this to times by, so that would create this expression. Final answer is the fifth root of a cubed on top, and on the bottom, an a. Number 43 is a pretty complicated one. There's all kinds of stuff to deal with. How about we take care of the negative exponents as our first step? So we have this fifth root symbol, but then inside there, I think we can do some work. A negative sign raised to a negative power makes a positive answer. R to the negative 10 raised to the negative 4 is R to the positive 40. And 243 raised to the negative 4 creates a reciprocal and moves the 243 up into the top with the letter R, and it now has a positive 4 power. It's not really necessary to write a positive sign, and it's not really necessary to write a 1 in the denominator. So let me rewrite this. What I'm saying is this original fifth root radical is equivalent to this one here. Next step, let's try to take the fifth root of what's inside the radical. But because the power on the 243 is not a multiple of that index, that will not produce an integer output. So let's do some rewriting. The number 243 is 3 to the fifth power. Then we can multiply the exponents together, creating 3 to the 20th power. What I'm saying is that 3 to the 20th power is the same thing as 243 to the fourth power. Now the power on the 3 is a multiple of that index. The fifth root of 3 to the 20th is 3 to the fourth power. The fifth root of R to the 40th is R to the 8th power. Notice how I'm figuring out these exponents. I'm dividing this power by the index. That made 4. I divided this power by that index. That made 8. 3 to the fourth power is 81, so the final answer is 81 R to the 8th. Finally, number 51. We're asked to rationalize, but the directions say to rationalize the numerator. That's kind of the opposite of what we normally do when we have radicals that have fractions. We want to make sure the numerator is a rational number. No radical symbols in the numerator. So first up, let's separate it into a separate numerator and denominator. Now let's rationalize the numerator by multiplying by square root of 3a on the top and on the bottom. The square root of 3a times the square root of 3a makes 3a. And in the bottom we have the square root of 15a. Here is the answer where it's the numerator that's been rationalized.